Hi everyone, I am Shifa. Here I am going to discuss the topic Illiac-Iv and the BSP. First, Illiac-Iv. The Illiac-Iv was the first massively parallel computer. The system was originally designed to have 256 64-bit floating point units and 4 central processing units able to process 1 billion operations per second. Due to budget constraints, only a single quadrant with 64 FPUs and a single CPU was built. The concept of building a computer using an array of processors came to Daniel Slotnick while working as a programmer on the IAS machine in 1952. Slotnick moved to the University of Illinois and joined the Illinois Automatic Computer team. With funding from Advanced Research Projects Agency, they began the design of a newer concept with 256 64-bit processors instead of the original concept with 1024 1-bit processors. When the first 64-processor quadrant of the machine was completed in 1972, it was sent to the NASA Ames Research Center in California. After 3 years of thorough modification to fix various flaws, Illiac-Iv was connected to the ARPANET-4 distributed use in November 1975, becoming the first network available supercomputer, beating the Cray-1 by nearly 12 months. Running at half its design speed, the one-quadrant Illiac-Iv delivered 50 MFLOP peak, making it the fastest computer in the world at that time. It is also credited with being the first large computer to use solid-state memory as well as the most complex computer built to date with over 1 million gates. Generally considered a failure due to massive budget overruns, the design was instrumental in the development of new techniques and systems for programming parallel systems. In the 1980s, several machines based on Illiac-Iv concepts were successfully delivered. The following figure shows the control units of the Illiac-Iv parallel computer. In Illiac-Iv, the PEs were upgraded to be full 64-bit processors using 12,000 gates and 2048 words of thin film memory. The PEs add 5 64-bit registers, each with a special purpose. One of these RGR was used for communicating data to neighboring PEs, moving 1 hop per clock cycle. Another register, RGD, indicated whether or not that PE was currently active. Inactive PEs couldn't access memory, but they would pass results to neighboring PEs using the RGR. The PEs were designed to work as a single 64-bit FPU, 2 32-bit half-precision FPUs, or 8 8-bit fixed-point processors. The new design had a total of 256 PEs arranged into 4 64 PE quadrants, each with its own CU. The CUs were also 64-bit designs with 64 64-bit registers and another 4 64-bit accumulators. The system could run as 4 separate 64 PE machines, 2 128 PE machines, or a single 256 PE machine. This allowed the system to work on different problems when the data was too small to demand the entire 256 PE array. Based on a 25 MHz clock, with all 256 PEs running on a single program, the machine was designed to deliver 1 billion floating point operations per second, or in today's terminology, 1 GFG flops. This made it much faster than any machine in the world. The contemporary CDC 7600 had a clock cycle of 27.5 nanoseconds or 36 MIPS. Although, for a variety of reasons, it generally offered performance closer to 10 MIPS. To support the machine, an extension to the digital computer laboratory buildings were constructed. Sample work at the university was primarily aimed at ways to efficiently fill the PEs with the data, thus conducting the first stress test in computer development. In order to make this as easy as possible, several new computer languages were created. Ivtran and Tranquil were parallelized versions of Fortran, and Gleipnir was a similar conversion of Algol. Generally, These languages provided support for loading arrays of data across the PEs to be executed in parallel, and some even supported the unwinding of loops into array operation. The Illiac-Iv system can be organized as in given figure. The Illiac-Iv system consists of the Illiac-Iv arrays plus the Illiac-Iv input-output system. The Illiac-Iv array consists of the array processor and the control unit. In turn, the array processor is made up of 64 PEs and their 64 associated memories, PEMs. The Illiac-Iv input-output system comprises the input-output subsystem, the disk file system, DFS, and the B6500 control computer. The input-output subsystem is broken down further to the CDC, BIOM, and iOS. CDC stands for Control Descriptor Controller and BIOM stands for Buffer Input or Output Memory, and iOS stands for Input Output Switch. The B6500 is actually a medium scale computer system by itself. As stated in the introduction, the original design of the Illiac-Iv contained 4 CUs, control units, and each of which controlled a 64 ALU array processor. The version being built by the Burroughs Corporation will have only one control unit which drives 64 ALUs as shown in figure. It is for this reason that Illiac-Iv is sometimes referred to as a quadrant, and it is these abbreviated versions of Illiac-Iv. Each element of the ALU array is not called by its generic name, but it is called a PE. There are 64 PEs and they are numbered from 0 to 63 as shown in figure. PE responds to appropriate instructions. If the PE is in an active mode, each PE has its own 2048 word 64-bit memory called a PE memory, PEM, which can be accessed in no longer than 350 nanosecond. Special routing instruction can be used to move data from PEM to PM. Additionally, operands can be sent to the PEs from the CU via a full word 64-bit one-way communication line, and the control unit has 8-word one-way communication with the PEM array. The input-output is handled by a V6500 computer system. The operating system, including the assemblers and compilers, also resides in the B6500 system. This is the functional block diagram of Illiac-Iv. Next, Illiac-Iv array. The control unit plus the array processor. There is a repertoire of instruction that can be completely executed within the resources of the control unit, and the execution of this instruction is overlapped with the execution of the instruction which drives the PE array. The control unit contains 64 integrated circuit registers called the Advanced Data Buffer, that is ADB, which can be used as a high-speed scratchpad memory. Each register of ADB is 64 bits long. The control unit also has a 4 accumulators registers called ACA0, ACAR1, ACAR2 and ACAR3, and each of which is also 64 bits long. Each PE is a sophisticated ALU capable of a wide range of arithmetic and logical operations. There are 64 PEs numbered 0 through 63. Each PE in the array has 6 programmable registers, that is A register, RGA or accumulator, the B register, RGB, which holds the second operand in a binary operation, the R or routing register, RGR, which transmit information from one PE to another, the S register, RGS, which can be used as temporary storage by the programmer, the X register, RGX or index register to modify the address field of an instruction, and the last one, D or mode register, RGD, which controls the active or non-active states of each PE independently. Each PE has its own 2048 word 64 bits per word random access memory called PEM. PE and PEM taken together are called a processing unit PU. There are 4 data paths by which data flow through the Illiac-4 array. These are control unit bus, the common data bus, that is CDB, and the routing network, and the last one, mode bit line. Next, the Illiac-4 array is an extremely powerful information processor, but it has of itself no input-output capability. This is the Illiac-4 input-output system block diagram. The input-output capability along with the supervisory system resides within the Illiac-4 input-output system. It consists of the input-output subsystem, a DFS, and a B6500 control computer. The input-output subsystem consists of the control descripted controller, that is CDC, the buffer input-output memory, BIOM, and input-output switch, IOS. And this is the total block diagram of Illiac-4 system. And the total Illiac-4 system consisting of the Illiac-4 input-output system and the Illiac-4 array is shown in the figure. All system configurations shown are transitory and more than likely will have changed several times in the next year or so. And the physical arrangement of Illiac-4. Each quadrant of the machine was 10 feet high, 8 feet deep and 50 feet long. Arranged beside the quadrant was its input-output system, whose system stored 2.5 GIB and could read and write data at 1 billion bits per second, along with the basic 700 computer that connected to the machine through the same 1024-bit wide interface as the disk system. The machine consisted of a series of carrier chassis holding a number of the small modules. The majority of these were the processing units, which contained the modules for a single PE, its PEM, and the memory logic unit that handled address translation and input-output. The PUs were identical, so they could be replaced or reordered as required. Next, the processor details of Illiac-4. Each control unit had about 30 to 4000 gates. The control unit had 16 64-bit registers and a separate 64-slot 64-bit scratch pad LDB. There were 4 accumulators AC0 through AC3, a program counter ILR, and various control registers. The system had a short instruction pipeline and implemented instruction lookahead. The PEs had about 12,000 gates. It included 4 64-bit registers using an accumulator, an operand buffer B, and a secondary scratch pad S. The fourth R was used to broadcast or receive data from the other PEs. The PEs used a carry lookahead adder, a leading 1 detector for Boolean operations, and a barrel shifter. 64-bit additions took about 200 nanosecond and multiplication about 400 nanosecond. The PEs were connected to a private memory bank, the PEM, which held 2048 64-bit words. Access time was on the order of 250 nanosecond. The PEs used a load or store architecture. The instruction set ISA contained 2 separate sets of instructions, one for the CU and another for the PES. Instructions for the PEs were not decoded and instead sent directly to the fins register to be sent to the PEs to process. The advanced instructions were decoded and entered the CU's processing pipeline. Next, the logical arrangement of Illiac-4. Each quadrant contained 64 PEs and 1 CU. The CU had access to the entire input-output bus and could address all of the machine's memory. The PEs could only access their own local store, the PEM of 2048 64-bit words. Both the PEs and CU could use load and store operations to access the disk system. The cabinets were so large that it required 240 nanoseconds for signals to travel from one end to the other. For this reason, the CU couldn't be used to coordinate actions. Instead, the entire system was clock synchronous with all operations in the PEs guaranteed to take the same amount of time no matter what the operands were. That way, the control unit could be sure that the operations were complete without having to wait for results or status codes. To improve the performance of operations that require the output of one PE's result to be used as the input to another PE, the PEs were connected directly to their neighbors as well as the ones 8 steps away. For instance, PE1 was directly connected to PE0 and PE2 as well as PE9 and PE45. The 8 away connections allowed faster transport when the data needed to travel between more distant PEs. Each shift of data moved 64 words in a single 125 nanosecond clock cycle. The system used a one address format in which the instructions included the address of one of the operands and the other operand was in the PE's accumulator. The address was sent to the PEs over a separate broadcast bus. Depending on the instruction, the value on the bus might refer to a memory location in the PE's PEM, a value in one of the PE registers, or a numeric constant. Since each PE had its own memory, while the instruction format and the CU saw the entire address space, the system included an index register to offset the base address. This allowed, for example, the same instruction stream to work on data that was not aligned in the same locations in different PEs. The common example would be an array of data that was loaded into different locations in the PEMS, which could then be made uniform by setting the index in the different PEs. And the next topic is BSP, Burroughs Scientific Processor. Early in 1973, Burroughs assembled a select team to design a commercial supercomputer. In 1977, the team's efforts resulted in the Burroughs Scientific Processor (BSP). It consists of an instruction processor, a set of parallel arithmetic elements, a main memory, an instruction or control memory, and a single input-output device. The BSP is a very high-performance system, and it is in the supercomputer class of machines and will deliver floating point results up to 50 into 106 operations per second. The BSP is a total system. It combines the general purpose processing capability of a Burroughs large scale or very large scale system with exceptional floating point capability. The BSP enjoys high reliability, availability and maintainability and is exceptionally cost effective. There is a large degree of extensibility inherent in the BSP design. The system has an impressive potential for modular growth. The BSP is a SIMD architecture. Here provide the block diagram of BSP system. BSP system consists of the system manager and the scientific processor. System manager supports networking and data communications and has a complete set of peripherals including printers, disks, tapes, etc. and that can be extended to include archival storage. And the system manager has a central processor and input-output processor and also has a set of terminals. BSP system consists of the system manager and the scientific processor. The system manager schedules and allocates tasks to the scientific processor. The scientific processor consists of the control processor, the parallel processor and the file memory. This is the BSP system diagram including system manager and scientific processor. This is the diagram of scientific processor of BSP. It includes control unit, parallel processor and file memory. Control unit includes control processor memory, scalar processor, controller and maintenance unit, parallel processor control unit, and the file memory includes file storage unit, file memory controller. And the parallel processor includes parallel memory, alignment network and 16 parallel arithmetic elements. There are three basic models of the BSP. For the user who already has a B7 B700 or B7800, there is the basic BSP. For other users, the basic configurations are the BSP 7811 and BSP 7821. Basic BSP: 16 arithmetic elements, 500 to 24K words of parallel processor memory, a controller processor with 262K words of memory and 4 million words of file memory. BSP bar 7811, a BSP with a B7811 system manager. The B7800 has one central processor, one input-output processor, one maintenance processor and an operator display console with dual displays. BSP 7821, a BSP with a B7821 system manager. The B7821 has two central processors, two input-output processors, one maintenance processor and an operator display console with dual displays. Dual BSP interface adapters provide a connection between the BSP and both B7800 input-output processors. However, only one interface adapter is active at any one time. The other is used for backup or system reconfiguration. BSP key features. It includes a system manager, the SSP elements and a vectorizing Fortran compiler. The system manager is responsible for overall BSP job scheduling and control, through which program preparation and data input and output are accomplished. It serves as the device for interactive program preparation and debugging and provides archival storage. The control processor portion of the BSP is a high-speed asynchronous unit that controls the parallel processor and performs scheduling, file allocation and input-output management. It is characterized by an 80 nanosecond cycle time, 12.5 MHz clock and is equipped with 262K words of 40K MOS memory with an access time of 145 nanoseconds. The control processor also serves to interface the BSP with maintenance and diagnostic devices. Programs to be run on the BSP are compiled on the system manager using a vectorizing Fortran compiler, which is a significant part of the system software. It is used to maximize the efficiency of the BSP across a wide spectrum of scientific applications. Next, BSP organization. It consists of three basic units: control unit, parallel processor and the file memory. Control unit is made up of a scalar processor unit that handles setup of vector operations for the parallel processor. 262K words of memory in which the program to be executed is stored. A parallel processor control unit that sets up vector calculations and a control and maintenance unit that is used to interface the maintenance features of the system manager to the BSP. Next, parallel processor is made up to 16 arithmetic elements connected to a parallel processor memory by means of alignment network. The network is a crossbar switch that connects the parallel memory banks to the AEs and is used to guarantee conflict-free memory access. And last one, file memory, that consists of charge coupled device CCD, storage media and a file memory control unit. Next, the parallel architecture of BSP. The design strategy for the BSP is parallelism. The capability of the BSP to sustain high processing rates is achieved via unique parallel designs. The BSP comprises multiple processors arranged to operate in parallel. The combined potential of multiple processors is brought to bear on large computational applications. There are four types of parallelism are featured within this architecture. That is, four different classes of computation occur simultaneously. These four types of parallelism are: 1. The arithmetic performed by the 16 arithmetic elements. Second one, memory fetches and stores and the transmission of data between memory and the AEs. Third one, indexing, vector length and loop control computations in the parallel processor control unit. And the last one is the generation of linear vector operation descriptions which take place in the scalar processor unit SPU. The BSP is analogous to an efficiently operated business. The SPU and its control memory are the executive suite. The executive's instructions are passed to the administrative clerks in the parallel processor control unit. This unit then does the bookkeeping and keeps all the major components of the business as busy and as efficient as possible. This is the functional structure of BSP, and this is the figure represents the BSP array unit architecture, and this is the pictorial representation of BSP control processor and array session. These are all about the Illiac-IV and BSP architectures. Thank you.